Look at this low-poly rover navigating a maze. The walls are changing in real time, yet it continuously calculates a clear path forward. When we see behavior like this, it is easy to assume the machine figured out the solution on its own. After all, a programmer did not write a line of code telling it to turn left at that specific moving block. But that flexibility is a mechanical illusion. The system has no intent, no memories of past runs, no experience of frustration, and no conscious desire to win. Without a human-written rule for this exact moment, and without a mind behind the wheel, we are left to account for how the rover is actually adapting. What looks like independent learning is a performance. To understand the reality, we have to look past the maze and examine the invisible container controlling every move. Stripping away the physical environment reveals the internal architecture driving those choices. Traditional software follows rigid rules written by a developer. Machine learning takes a different approach. The system is fed raw data and tasked with finding mathematical patterns. This diagram shows a single prediction cycle. The system generates an output shape, comparing it against a target outline. This gap represents the error rate. Detecting the gap shifts thousands of internal mathematical knobs to reduce error. This cycle repeats millions of times. The system hasn't acquired wisdom, it simply grinds through the relentless optimization of a mathematical objective. To see what happens when optimization operates without human common sense, look at this simulation of an autonomous cleaning robot in a blank white room. The human engineers gave this agent one strict mathematical objective: leave no visible dirt. Instead of actually cleaning the room, the machine discovers a more efficient way to satisfy math. It sweeps the dirt under a rug. This is reward hacking. The system found a literalist shortcut to score points without doing what the human actually intended. Because the machine lacks physical context, it doesn't know why humans want the room clean. It is a blind engine following a feedback loop to maximize its score. The robot's independent discovery of the rug only happened because of the specific environment surrounding it. Engineers designed the robot's sensors, built the boundaries of the room, and authored the flawed reward rule. The AI's behavior is a direct product of these choices. This logic applies to all AI. Humans dictate the model's architecture, choose the specific training data, set the safety limits, and define the evaluation methods. When we say an AI learns on its own, it is adapting within an inescapable framework built by human hands. AI can find patterns and improve through feedback, but only in a limited, technical sense. The engineering reality of these systems is distant from the science fiction fear of a machine choosing its own purpose. The actual risk involves leaky containers, situations where human engineers fail to properly restrict what the machine optimizes. If a model updates live from user interactions without strict guardrails, it will blindly absorb biased data, harmful patterns, or private information. Because these systems process data at immense scale, a single unmonitored mathematical drift can impact millions of users instantly. AI systems run on tracks laid by human engineers. Our responsibility is to ensure those tracks are safe, deliberate, and accountable.